Morning, everybody. Welcome to Friday. Any big plans on the spring break? Panama. Working. Are you going home? Good. West Virginia. All right, Mackenzie, would you mind shutting that door, Brock? Oh, sorry. Sierra, shut that door behind you.
No, he says he has.
Okay, listen, so we'll probably wrap up this chapter next Wednesday, probably. Maybe on Monday. And then on Friday, we'll have a review for the test. And then on Monday, we'll have the test. Come on in, Tank. She's in your seat. Let's run off out of there. Okay. So anyway, we're here on the 12th. We'll have 3 days when we come back before the exam, and then I'll hand that back to you on that Wednesday. So we started on sound, speech, and hearing. We'll actually get into a little bit of the human body and how the ear works at the end. We talked about the difference between transverse waves go up and down. Longitudinal waves go side to side. And so sound waves are longitudinal waves. Sometimes we'll also call these compressional waves. I'll talk about that later. So longitudinal or compressional. Now a little bit about simple harmonic motion, because this describes how we think about sound waves, and so we need to know some of the terminology. Simple harmonic motion is just where something oscillates with a force that's proportional to the distance from the equilibrium position. We saw that with a spring. You remember springs, the whole F equals kx business? So often springs are used to describe simple harmonic motion. But it's where something oscillates with a force, or sometimes we'll call this a restoring force, that is proportional to the distance from an equilibrium position. That's my abbreviation for equilibrium. So we talked about springs last semester. If I have a spring, if I pull it a certain distance down and then I'll let it oscillate, it'll oscillate because as it goes down, the force increases, pulling it up. That force increases, decreases, increases, decreases, increases, and decreases. And it depends upon the distance from the equilibrium position. If you have a bigger distance, then you have a bigger force. And we described that with the force on a spring. And sound is also simple harmonic motion. We'll see that sound similarly has a restoring force that has to do with its medium. So it's sort of like the medium is elastic. If I push on it, then it pushes back on it. So the air that we're speaking in right now, or that I'm speaking in, is elastic, and so if I push on it, is there a problem over there? Sorry. No? Okay. All right. That there is an elastic medium. The restoring force then for sound is the pressure of the surrounding medium. So we can think about our medium consists of particles. These are my very regularly spaced gas particles. And if I take one of these particles and I displace it in some way, the other particles are going to push on it and force it back into its position. So we'll have one force, say the pressure of my voice or whatever sound it is that you have, will push it in one direction, but then these other particles will all force it back into its same position. So the medium has this pressure that acts as the restoring force, pushing a particle back into its original position. Need to know a few definitions: equilibrium, amplitude, period, frequency, and wave speed. And need to know how to calculate some of those as well. We'll look at two different graphs for sound, or for simple harmonic motion. One is the snapshot graph, and this looks at our displacement versus position. Now both of these graphs are going to look the same, but they actually describe different physical properties of our waves. So the snapshot graph is at a particular time. It's like you take a picture of the wave and you take a snapshot of it at a particular time. And the graph will look something like this. For our simple harmonic motion, we need to know a few of these properties that we use to define a wave. This is a wavelength, one wavelength. We've already seen wavelength, but it's the distance from one point on the wave to the next point on the wave. So that's a wavelength, for example. Is this a wavelength? No, that would be a half wavelength, in fact. This is a full wavelength. So you want to take one point on the wave over to that same point where it begins to speed again. Bless you. We also want to know the amplitude. The amplitude is this distance from the middle of the wave up to the peak or down to the trough. That's our amplitude. And that's it for the snapshot graph. Now we can also look at a wave as it proceeds through time, and that's a history graph. This is a picture of the wave as it proceeds through time. But it looks the same. It looks a lot the same, in fact. And we have our displacement of the wave on the y-axis. So this is still going to be my amplitude. But the time, notice this is a time now. This is no longer a wavelength because on the x-axis I'm dealing with time. This is going to be the period of the wave. So the period is the time for the wave to travel one wavelength. And we get that from our history graph. Notice these look very similar. They look the same, in fact, but they're different. They're measuring different things. The snapshot graph is a snapshot at a particular time in space, or a particular time. And the x-axis here is the position. What position is the graph in? And then the y-axis is the displacement. So we can figure out the wavelength from that graph. Gosh, bless you. And then the history graph shows the wave as it proceeds through time. So we can still get the amplitude from this graph, but what looks like the wavelength that we found in the previous graph is really the period. But the period and the wavelength are related. Usually we use a capital letter T for period. And we can calculate some things with the period. First of all, the speed of the wave. If we travel one wavelength in one period, then the speed is equal to the distance over the time. That's going to be the wavelength over the period. And then we're also going to define the frequency. And the frequency is 1 over the period. Our frequency will be related to pitch, as we'll find out later, that we have low frequencies and then we have high frequencies. You want to see like my one trick? Like this is my one skill that I have. I'm not a very skilled person, but I can do this. And it's not as easy as it seems. Low, high, low, high. Can y'all do that? You can't, can you? Like nobody's even going to try.
I don't know what you did to try and do it. I totally like.
Oh, you would just do it?
No, like I don't know what your trick was. I don't understand.
Oh, I said low, high. See, I'm saying low, but I'm giving it a high pitch. And I'm saying high, but I'm giving it a low pitch. It's like patting your stomach and rubbing your head at the same time. It's not as you try it at home. Yeah, Jordan, that's impressive. Okay, so the frequency is 1 over the period. And then we can also relate, because of these relationships, we can relate the speed of the wave by the wavelength and the frequency. So we'll look at this and we'll use this expression quite a bit. Now, we'll find that the speed of a wave is not dependent upon the wavelength or on the frequency. Actually, let me go and write that. It'll come up later. But V is not dependent on lambda r on the frequency. And so you're probably freaking out. You're like, you just wrote right here that the speed of the wave is equal to the wavelength times the frequency. But the speed of the wave is always constant. And if I change my wavelength, then the frequency would change in response. If I change my frequency, the wavelength of the wave will change in response. The speed will always be constant. The only way to change the speed is to change the medium. We'll see that later, or why that's important. But I'm just going to throw that out there. Okay? So you'll need to know how to find those various things, how to, like, define them from a graph. Like if I give you a snapshot or a history graph, how to figure out the period or the wavelength or the frequency or the amplitude. And then also be able to calculate the speed given the wavelength and the frequency. Let's try a few of these quicker questions. Which of these is the wavelength of this wave? We're doing this one on the left here. All right, well, let's stop at 115. 115. Oh man, okay, B is right. B goes from this point over to this point. That is one full wavelength. I go from one point on the wave over to the same point over there. Or I could say the wavelength is here. I could say the wavelength is from here to here. All of those would be measurements of the wavelength. What was the other common answer that y'all gave? Yeah, C was sort of the next thing. C goes a little bit too far, so C is too far. You get like 1 1/4 wavelengths there. Let's do this one on the right, which has the higher frequency of these waves. It's this room. I think you're right. Like my students study forward, but they don't listen to music really as much. I should do an honors thesis on that. Dr. Ducey would love that. All right, let's do 50 seconds. Okay, good. A is right. Hey, what's the worst part about living on O Street? You have to walk a whole block. Y'all remember that one? I told you that one last semester, I think, didn't I? You don't remember it? Okay. What? A different one? I don't, I'm running out of jokes. We got like 3 days left, so I'm just hanging on, okay? What? Yeah, send me jokes, that's fine. I would take. Answer the question. Let's see which one. And yours was an, I used it last time, the tractor down. That was a good one. Okay, we're doing, during a time of one period, a wave travels what? All right, let's stop at 105. 105. All right, B is the right answer. In one period, or wave travels one wavelength. And then let's try this last one. Sound is a what type of wave? Is it a simple, transverse, compressional, or is it a hand wave? All right, let's stop at 33. 33. Okay, good. Hey, what's the difference between roast beef and pea soup?
What?
I know I told it last semester, but y'all don't remember it.
I do.
Anybody can roast beef. Sound is a compressional wave. You can also call it a longitudinal wave. Okay, so sound of a vibrating string. In musical instruments, the larger instrument is usually, what, higher or lower in pitch? Right. What instrument did I play? I played the tuba and the trombone. Right. So the instrument is usually lower in pitch. So for example, you know, the tuba versus the piccolo. The piccolo is a little bitty thing, right? It's like this big, but the tuba is big, big thing. So usually bigger instruments are lower in pitch. Almost always, I think. The pitch is proportional to the frequency. So when we talk about the pitch of an instrument or of any sound, we're talking about its frequency. And the volume of our sound, whether it's loud or quiet, is proportional to the amplitude. It was that way with light too, right? That when we had a higher amplitude, that is when our two waves added up to give us one with a bigger amplitude but the same frequency, the amplitude got bigger, it was brighter, right? And so the similar thing with sound, that when it's a larger amplitude, we have a bigger volume. Now for a vibrating string, we have this expression for the frequency. The frequency is equal to 1 over 2L times the square root of T over mu. And here L is the length, T is the tension in the string, and mu is the mass density. It's the mass density, but we can think of it as the mass too, if that would help. But it's the mass per unit length. So I have the length, the tension, and the mass density. Now you'll have this equation, of course, and I might give you some values for LT and mu and ask you to calculate the frequency. These are going to be in units of meters, newtons, and then this is going to be kilograms per meter. And then that'll give us our frequency. I do want you to notice the relationships, because that's really what I'm concerned about here. That if L increases, what happens to the frequency? If I make the length of my string, my vibrating string, if I make it longer, what happens to my frequency? It goes down, right? I get a lower pitch. So if my length gets bigger, my frequency goes down. If my tension increases, if my frequency increases, or excuse me, if my tension increases, my frequency also increases. If you ever tuned a stringed instrument, you might ever tuned a stringed like a piano or a guitar or whatever, you have on a guitar you have those keys that you twist that stretches the string out. When you do that, the pitch goes up. When I increase the tension in a string, the frequency increases. And then if the mass density increases, if my strings get heavier, then the pitch goes down, the frequency goes down. That's why I play bass guitar. And on the bass guitar, it's different from a regular guitar in that the strings are just a lot bigger. You ever seen the strings on a bass guitar? They're like 2, 3, 4 times bigger than a 6-string guitar. They're also longer, so they have a bigger mass density, which makes the pitch lower. And then they also have longer length, which also makes the pitch lower. And then you can change the tension in them to adjust for tuning the instrument. All right, so you'll need to know, well, let's see, I have some rubber bands. You can see this. Really, you can just sort of see the tension, but you can play around with this and figure out how the length of the string changes too. But notice if I have a rubber band, it makes a sound. I do that. But now if I keep it the same length, but make it tighter, down here, it's a lot louder. I'll pass these rubber bands around. These are special compartment rubber bands. So
Be careful. Lots of careful to get
there's some. There's some. All right. So for a vibrating string, you can change the tension, and it'll change the frequency of the sound. All right. Now let's look at the speed of sound. The speed of a wave does not depend on either the pitch, that's the frequency, or does it depend on the volume? That's the amplitude. It depends only on the medium. It also, by the way, doesn't depend on wavelength, not on wavelength either, even though we said before that the speed of a wave is equal to lambda times frequency. That is not dependent on the wavelength, the frequency, nor is it dependent on the volume or the amplitude. But it's only dependent on the medium. So a high-pitched sound will not necessarily have a faster speed. The speed depends on the elasticity of the medium. More elastic medium means a higher speed. Which do you think is more elastic? Let's do this as a clicker question, and then I'll tell you the answer, but I just want to know what you think. Which is more elastic? Air, water, or some solid like steel? Which is more elastic, a gas, a liquid, or a solid? Which is more elastic? Now the elasticity is going to describe the force, the restoring force. So the more elastic material will have a bigger restoring force. Also, the more elastic material will have a higher speed of sound. All right, so let's stop at 52. Okay, good. C is right. Steel is a more elastic material. Solids are almost always more elastic. You can think about it. If I have a solid, and it's made up of atoms, solids actually have a very regular structure in their atoms. If I displace one of them, it's going to be really, really hard to displace an atom in a solid material. It has a really big restoring force because that solid, because of the nature of its structure, is going to want to go back to its original position. So it has a really big restoring force. In air, sound travels at about 340 meters per second. And it travels faster in water and in steel. In water, it travels about 1,500 meters per second. And in steel, I think this is right at, it's about 6,000 meters per second. Gosh, I think it's faster than that actually. It's a lot more than in air. I think it's more like 13,000. But we'll just say that. The number's not important. It's just that it's bigger. Let's see, I have a video I want to show you. This is put out by the APT, and it's about audio triangulation. Are y'all aware that you triangulate with your ears? Yeah, so you can, like, everybody close your eyes. Everybody close your eyes. Close your eyes. Now, keep your eyes closed and point where I am. Yeah, now you know. That's pretty good. Like, you're able to tell where I am just by the sound that I make. Plus all the squeaking and Juliana open her eyes. And the back half of it, like, y'all didn't shut your eyes at all. It's like we're not even part of this class. But, so anyway, this video is about triangulation and how that works in humans, and then also how it works in animals like sharks, which live in water. It has to happen a lot differently. It's in different media. Let's see, we've already done this one. Let's do the one on the right. The answer to this, by the way, was A, but we've already done it. Let's do the one on the right. The speed of the wave depends on which of these? Are there homework questions for this guy? I don't think there are. Okay, good. All right, we'll stop at 35. 35. Okay, good. C is right. It's dependent only on the medium. So C, 3 only. Hey, why did the boy eat his homework? Because his teacher said it was a piece of cake. Okay, so production of sound. Sound waves are created by some object pushing on the air. In fact, you know, that's how a speaker works. A speaker, you have this cone, and then you have this electromagnet, and it pushes on the cone, and you create this pressure wave. It actually physically pushes on the air at a particular frequency. And you know, when you have those bass big woofers, are those a high or low frequency? They're a very low frequency, and that's why you can actually see them, because they push at a very low frequency, so you can actually see them vibrating. And you know, the little speakers, the tweeters, or the higher frequency speakers, they oscillate at a much higher frequency, so you can't really see those vibrating. But that's how sound waves are created, just by some object pushing on the air, and that's how we create sound as well. We're going to think about 2 different kinds of waves. A simple wave has a single frequency. So a simple wave would be the speaker would just push with a single frequency. But a complex wave, on the other hand, which is most sounds, has multiple frequencies added up. So my simple wave would just have our simple waveform like this, but a complex wave would be made up of a lot of different things, and you know, it might look like really funky. You might have something like this, something that is periodic but is not nearly as simple as what we have here, that it's made up of a bunch of different waves with different frequencies that are all added up. So you can do this with a sound generator, and we'll play around with the sound generator a couple more times, but let me just show you. There are a bunch of these, but we'll just use this one. Oh, that's annoying, right? All right, so that's a single simple wave. Does that annoy anybody? 75 hertz? Okay. Then I can add multiple waves And what it's doing is it'll add these different waves together. And so I create a more complex wave that is not a single tone, but there are actually lots of variations within the tone. And now a sound like you singing or just sounds of people speaking, that will have tens, 20, 30, hundreds of different frequencies all mixed in together. And that's how humans and that's how musical instruments create this very rich range of different types of sound. Okay, this is a type of interference where we get these sound waves that actually add up of these different frequencies. We'll come back to that in a bit, and I'll show you more of this. So you have simple waves, and then you have complex waves, and most sounds are complex, but we'll deal with simple waves. Intensity of sound. Sound carries energy like all waves, and to characterize the energy, we measure the intensity, and we'll define it by this. Intensity is the power divided by the area, P over A. P is power. It's the same power that we had before. It's measured in watts. So it's in energy per unit time. And our area, of course, is in meters squared. So our units for intensity are going to be watts per meter squared. Remember, 1 watt is equivalent to 1 joule per second. Just to remember back chapter 4 or 5 that we had last semester. Now, if we assume a source is a point source, that means that it's emitting sound in all directions. And this isn't real common, actually. It's kind of hard to get a true point source because if you think about it, when you speak, you have sound just coming out sort of in a cone coming from your mouth. But if you think of a true point source, this is sort of a point source because the sound is emanating outward from my hands in all directions. So if we assume that the source is a point source, then we can write the intensity in this way. The intensity is just going to be the power over the area. Right, so here's my point source, my area. I have a radius r. My area is going to be P over 4 pi r squared. This is the area of a sphere. The point of this is, though, is that the intensity and the distance from the point source is going to be an inverse square type relationship. Here r is the radius of the sphere. And as r increases, I goes down. So if we think about, if we draw the value for I and r, it's going to look something like this. It's an inverse square relationship. So if I move twice as far away from the object, then my intensity will drop by a factor of 4. Okay, because, well, if I increase r up here by a factor of 2, say, because it's squared, I decrease the intensity by a factor of 4. It's an inverse square law. We've seen inverse square laws a lot. They exist a lot in nature. They exist because of spherical symmetry of a lot of things, that we get this inverse square relationship. Okay, dokie? You're good? Okay, let's try these quick tests. Does somebody have it here? Who has one? Nick, you have one? Okay. We might be up in just a second. All right. So let's stop at 50, I think. 50. Looking pretty good. Just a few more seconds. Okay, good. Sorry. Next one, maybe. All right, so D is right. Because I is equal to power over 4 pi r squared. If I move from 1 meter to 2 meters, I've doubled my distance, then I'm going to be at 1/4 the original intensity. So how is intensity defined here? All right, let's stop at 30. 30. Okay, awesome. D is right. It's power over area. Nick, you got us a joke? A short one, okay.
I don't know.
Oh, does anybody have a short joke? Like a one-liner? Huh? Well, her GPA. No. Anybody one-liner? All right. It's going to be power over area. All right, let's look at the reference points. I got 2 reference points that are important when we look at human hearing. Human hearing, we have 2 reference points. One is the threshold of hearing. What's the quietest sound that you can hear? And then we have the threshold of pain. What is the loudest sound that you can hear and experience pain? When do you first begin to experience pain? Have you ever experienced pain when you're hearing something that's too loud? Yeah, maybe so. So these are different for different human beings, but typically these are about 10 to the minus 12 watts per square meter. And then watch this. The threshold of pain goes all the way up to 1 watt per square meter. You have 12 orders of magnitude between the lowest sound that you can hear and the loudest sound that you can hear. That is remarkable. 12 orders of magnitude. 10 to the 12th. That's what, like 100, 1,000 billion times the lowest intensity to the highest intensity. 10 to the 12th. Like the human ear and the human eye are both very remarkable as far as detectors, just looking at them as detectors. The human eye, too, can similarly detect light of such vast range of brightness. Did you know if you close this room and you had no light in it and you just let 1 photon go in this room, that the human eye could detect a single photon? Did you know that? It's true. And then you can also walk outside on a sunny day and still see just fine. So the human eye is remarkable in the amount of light that it can detect. We don't have anything like it. Like you can have a detector that detects a single photon, or a detector that detects a sound this low. But if you were to put upon it either a lot of light, it would just completely burn it out, or if you were to put on a sound this high in volume or in amplitude, it would blow it out. It wouldn't work. So anyway, pretty remarkable. These aren't exact for everybody, but they're dependent on the person, and then they're also dependent on the frequency to which that person is most sensitive. Some frequencies are just, they hurt your ears a lot more, right? Like, for example, that one's not too annoying, but that one, annoying, right? You can't hear 1 hertz. We'll get to that in just a second. Okay? So that brings us to sound intensity level, and students often get messed up on this. If you're taking the MCAT, you might see it there. I think they like doing logarithms for some reason. But the sound intensity level is what we use to describe the range of sound that we can hear, how loud a sound is. And the reason we use it is because we can hear sounds over this wide range. So if the intensity of a sound is 10 times that of another sound, it has 10 times the intensity. The person perceives it only to be about twice as loud. Because of this, we use a logarithmic scale to measure loudness, and we call this not the sound intensity, but we called it the sound intensity level. So it's a little bit different. Why don't I have beta here? I'm going to call this L, okay? So L is equal to 10 times the log of I over I naught. So this I naught, this is our threshold. The lowest sound that you can hear. This is measured in decibels. I don't know if you remember, we didn't really do this prefix. You don't see it very often. But the prefix deci is actually 10 to the minus 1. So really, the unit for sound intensity level is the bell, but we use decibels. There's a story behind this. I forget what the story is, but you can Google it. I forget. There's some story. But a bell is your unit for sound intensity, and so we use decibels. That's where this 10 comes in right here, because we're giving decibels and not bells, so that 10 comes in there. All right, I naught is the threshold for hearing. That's that 10 to the minus 12, and we can compare two sounds like this. I1 to I2 is equal to 10 times delta L over 10. Let me just give you a little bit of reminder about logarithms, because it'll probably come up on the test. Let's say that I have n equals a to the x. All right, so then I would say that 100 equals 10 what? What would x be? 10 what is 100? All right, 10 to the 2, 10 squared. And 1,000, for example, would be 10 cubed. So the way I work with these logarithms is I say that the log base a of n equals x. And so the log base 10, and a logarithm is base 10 most of the time, of 100 is equal to 2. You see our x value is right here. This is our a value, and then this is our n value. The log base 10 of 1,000 is equal to 3. And on and on. The log of 10,000 is 4. The log of 100,000, what's this equal to? It's equal to 5. I can just count the number of zeros if it's a factor of 10, and that'll tell me the logarithm of it. So if I have, I can compare two sounds. Say I have I1, sounds I1 and I2. They're going to be equal to the difference in the decibels divided by 10, 10 to the difference in the decibels divided by 10. So a change in 10 decibels results in a sound that is 10 times as intense, right? If I let delta L equal 10, then I1 over I2 equals 10 to the 10 over 10. That I1 is 10 times as intense as I2. Y'all with me on this? Logarithms? You've seen logarithms, but probably a long time ago, and you biologists probably use them as well because they come important in some systems. 30 decibels is 10 times as intense as 20 decibels. 50 decibels is 100 times as intense as 30 decibels. What about 70 decibels? How many more times intense is it compared to, say, 110 decibels? Or no, let's do 30 decibels. How many times more intense is that? 10,000 times more intense. Yeah, right, because every time I increase by 10 decibels, I increase by a factor of 10. So I've increased by 40 decibels, and that translates into an intensity of 10 to the 4 times intensity. Y'all follow me on this? it all comes about from this expression right here, comparing two intensities of sound. There are some homework problems, I'm pretty sure, that have to do with this, but we'll work through one right here, where you have to figure out what is the difference in the intensity giving the decibels. It's not always as simple as this. Like, say, for example, I have two intensities that are in ratio of 2 to 1. So I1 to I2 is in ratio of 2 to 1. I1 is twice as intense as I2. Well, I would say 2 over 1 equals 10 to the delta L over 10. Let's say the log of 2 over 1 is equal to the logarithm of 10 to the delta L over 10. Listen, y'all done logarithms because we used natural logs last test, right? Y'all did the natural logs. Although when you're doing natural logs, the natural log of e to the x is equal to the x. The natural log is just a logarithm base e, whereas a logarithm is base 10. So when I do this, when I take the log of this, it's like that cancels out. The log of 2 is equal to 0.3. I just did that in my calculator. And that's going to equal to delta L over 10. So delta L then is going to equal to 3. That means that I1 is 3 decibels higher than I2 in sound intensity levels. I1 is 3 decibels higher than I2. Louder than I2. Again, there's some homework for this for you to practice doing your logarithms and your decibels. Okay? Can I go down from here? Practice that. Look at the old test. Look at sort of what I quiz you on. Let's look at the Doppler effect. This comes up a lot in the MCAT preparations too, and that's really the main reason I threw this in for you MCAT folks, because we don't usually do sound, and it often gets left out of physics courses, so sort of want to do some surveys of it. When the source of a sound is moving, the observer perceives a frequency that is different from the actual frequency. You've all probably experienced this, like you hear a fire truck or a police car or something with their siren going, and it's coming towards your house, and then it zooms past your house at a pretty high speed. You hear it go, the frequency increases as it comes closer to you, and then as it moves away, the frequency decreases. You can hear this with trains too. If you've ever heard a train coming towards you with its siren or its horn going or whatever. So if I have, say, a police car, coming towards me, it's emitting this sound. If I'm standing over here, it emits a certain sound, F1, but over here I hear a certain sound, F2. And the frequency that I hear will be bigger than F1 because of what we call the Doppler effect. That as this car is coming towards you, it's actually physically pushing these compressional parts of the wave together, because it emits a wave front and then it moves forward a little bit, and emits another wave front and it moves forward. And the faster it moves, then the more it's going to compress those wave fronts and give it a higher frequency. And we can calculate what those frequencies should be. If the source is moving, then the observed frequency is equal to the frequency of the source times the velocity of the wave divided by the velocity of the wave plus or minus the source. All right, how do you know if it's going to be plus or minus? Right, one of them will give you a frequency that's lower, and one of them will give you a frequency that's higher. If it's coming towards you, if the source is coming towards you, then you want the one that gives you the higher frequency. See, I always forget which of these will give us a higher frequency, the positive or the minus. The minus, yeah. So if I make this number smaller, it makes this value bigger. So if it's coming towards me, I'm going to use the minus. If it's going away, I'm going to use the plus. Because the minus gives me a higher frequency obs, and the positive will give me a lower frequency. So that's really just want to ask yourself, when you come across a problem like this, well, first ask yourself, well, should my frequency be higher or should it be lower? If it's coming towards me, it should be higher. If it's going away from me, it should be lower. And then you'll probably be able, you might even be able to select out the answer at that point. But just ask yourself that. These equations, of course, are on the equation sheet. Now, similarly, if the observer is moving, because that can happen too, then it's equal to the frequency of the source times the velocity of the wave plus or minus the velocity of the source divided by the velocity of the wave. And here it's going to be opposite. So towards will be positive, away will be negative. Don't try to memorize the plus minus business. Just remember, if it's coming towards me, it's higher frequency. If it's going away from me, it's lower frequency. And then finally, a sonic boom. Oh, gosh, we're almost out of time, huh? A sonic boom occurs when the speed of the source approaches the speed of the wave, approaches or exceeds the speed of the wave. Blue Angels are coming to New Orleans next weekend, and so they'll probably produce a sonic boom because those planes will exceed the speed of the sound wave, and the crest of the wave will actually compress. We'll talk more about that later. But y'all have a great day, okay? Have a good break.